So in the previous lesson, we looked at how to find the product of three vectors. Specifically, we looked at how to find the scalar triple product. And in today's lesson, we are going to do a little bit of application. Now, sometimes you can be asked to show whether or not a given set of vectors is either linearly dependent or linearly independent. And that is exactly what we are going to do in today's lesson. Now, a set of vectors, let's say ABC, is said to be linearly dependent if and only if one of the vectors is a linear combination of at least one of the two remaining vectors. So let's say if we consider the vectors ABC, if A is a linear combination of only B, or if A is a linear combination of B and C, then we say that the given set of vectors ABC are linearly dependent. So a given set of vectors ABC are said to be linearly dependent, coplanar, or even collinear if the scalar triple product is equal to 0. Now, on the other hand, if the scalar triple product is not equal to 0, then we say that the given set of vectors are linearly independent, or better still, non-coplanar. Now, one important thing we need to take notice of is the fact that for a given set of vectors, let's say ABC in order, 1. If the scalar triple product is greater than 0, then the set of vectors constitutes a right-handed system. And if the scalar triple product is less than 0, then we say that the given set of vectors constitutes a left-handed system. So here we have a question. We are going to show whether or not these sets of vectors are coplanar. Now, we are given the first set of vectors, so for I, and then we have the second set of vectors, II. Now, what we are going to do literally is to find the scalar triple product of these vectors, the set of vectors. And then if the scalar triple product is equal to 0, then we say that the given set of vectors are coplanar. And then if they are not equal to 0, we just conclude that the given set of vectors are non-coplanar. So let's do that together. So for I, we have the set of vectors, vector A. We are basically going to write the coefficients of ijk. So we have vector A, coefficients we have 1, 3, 2. Vector B, we have coefficients 2, 1, 4. Vector C, we have coefficients 4, 7, 8. Now let's try to find the scalar triple product. So that is given by A dot into bracket B cross C, and that is given by the determinant of a 3 by 3 matrix. And for each row, we are basically going to write down the coefficients of A, B, C in that order. So for row 1, we have coefficients 1, 3, 2. Row 2, we have 2, 1, 4. And then for row 3, we have 4, 7, 8. Now let's try to find the determinant of this 3 by 3 matrix. So that is equal to, we select the first element in row 1, so that is 1, and then we cancel out the row and column containing this element. We are left with 8 times 1 minus 7 times 4. So 8 times 1 is 8, 7 times 4 is 28, minus, we have the second value, that is 3. And then into brackets, we cancel out row and column. We have 8 times 2, which is 16, minus 4 times 4, which is also 16, and then plus 2 into brackets. We cancel out row and column. We have 7 times 2, which is 14, minus 4 times 1, which is 4. Now let's simplify further. So we have 8 minus 28, which is negative 20. So times 1, we still have negative 20. And then here we have 16 minus 16, which is 0. 0 times negative 3 is still 0. And then here we have 14 minus 4, which is 10, times 2, which is 20. So plus 20. And then negative 20 plus 20 is 0. Therefore, since the scalar triple product is equal to 0, it follows that the given set of vectors are coplanar. Now let's try for the second set of vectors. So for I, we also have vector A having components 2, 1, 4. Vector B, we have 1, 2, 1. Vector C, we have 4, 3, 6. Let's try to find the determinant, or better still, let's try to find the scalar triple product that gives rise to the determinant of the 3 by 3 matrix containing elements. For row 1, we have coefficients of vector A along the x, y, z axis for vector A. So we have 2, 1, 4. Vector B, 1, 2, 1. Vector C, 4, 3, 6. So that is given by, we select 2, we cancel out row and column containing 2. We have 2 into bracket. 6 times 2 is 12, minus 3 times 1 is 3, minus 1. We cancel out row and column. We have 6 times 1, that is 6, minus 4 times 1 is 4, plus 4. We cancel out row and column. We have 3 times 1, 3, minus 4 times 2 is 8. Now let's simplify further. So we are going to have 2 times, this becomes 9, minus 1 into bracket, 2, plus 4 into bracket, negative 5. So this is equal to, we have 2 times 9 is 18, minus 1 times 2 is 2, and then 4 times negative 5 is negative 20. Now 18 minus 2 is 16. 16 minus 20 is negative 4. So negative 4. Therefore, since the scalar triple product is not equal to 0, then it follows that the set of vectors are non-coplanar. They are non-coplanar. So that's it for today's video. Thanks for watching and see you in my next video. Bye bye.